you know, if you go over, it just takes time out of, you just eat less, right?
I'm going to start getting angry if I go too much past 1:30. Or at least cranky. I'm kind of hungry. Okay. So, well, that was a really nice talk and a good warm-up for my talk, because I'm going to talk about another approach to Bootstrap, which is special to 2 dimensions. And that's the been called a modular bootstrap. The basic idea here is similar to what David and others do with crossing symmetry, but it's to use modular invariance rather than crossing symmetry as your guiding principle. And instead of looking at 4-point functions, we're looking at much simpler correlation functions, although higher point functions could be studied as well, which is you study the partition function of a CFT. So let me just say what I'm talking about. I'm talking about 2D CFTs, and they should be unitary and modular invariant. Okay, so 2D CFT has the central object is going to be the one-loop partition function. And we're going to exploit modular symmetry, which says that we're on this torus with modular parameter tau. It says that z of tau should be z equal to z of minus 1 over tau. There's also another modular symmetry, which is tau goes to tau plus 1. We don't really know how to use this, how to make full use of this part of the transformation. So really, we're just looking at this Z2 symmetry of the partition function. And we're going to have 2 different expressions for the partition function. We're going to set them equal to each other, and we'll get equations which are reminiscent of the equations that crossing symmetry gives us between S and T channels of 4-point functions. And we'll use these in the same way. We'll use them to constrain operator dimensions, and we're also going to use them because you have so much more information, explicit forms of the conformal blocks in 2 dimensions, etc.
Are you assuming there are 5 number of blocks? Are you assuming a rational theory?
In fact, most of the theories we talk about will have infinite number. We can also say a lot about the number of states in these theories and the spectral density. So this is, I'd say that this is a complementary approach to crossing symmetry, really, because when we study a correlation function in a CFT, we're talking about putting punctures on a underlying Riemann surface over which the CFT is defined. And crossing symmetry is going to exchange these punctures. And on the other hand, cycles of the Riemann surface, modular invariance is going to interchange the cycles. So these are both types of symmetries are required in order for the CFT to be defined consistently on arbitrary Riemann surfaces. And these symmetries fit together into the mapping class group of the Riemann surface. The modular symmetries and the crossing symmetries are subgroups of this mapping class
what
group.
does crossing symmetry do to the Riemann surface?
It just interchanges identical punctures. That's what crossing symmetry does. Okay, so we're studying complementary information to the crossing symmetry, and an eventual hope is maybe by combining modular symmetry with the crossing symmetry, we can learn even more about these conformal field theories than what I'm going to tell you about today.
So your theories are not even unitary necessarily.
What?
They're not even necessarily unitary.
No,
is
I
it?
said unitary.
Oh, is it?
Yeah, and that's going to be a crucial ingredient.
So then there's a constraint from the fact that when you expand Z, the coefficients are all positive integers.
That's exactly how you do it. Yeah. Okay. So the approach I'm going to talk about was originally, I guess, in some version of it was used by Cardy to prove a lot of interesting things, general facts about the spectra of CFTs back in the 80s, and more recently, Simeon Hellerman this was in maybe 2009. Used this approach to find information of exactly the same sort that David was talking about to constrain the dimensions of the operators with low-lying conformal dimensions, the primary operators. He proved a very interesting theorem, which is that in any CFT, unitary modular invariant, with an assumption, additional assumption, which was that the CFT with no chiral algebra or chiral currents in it. Okay, that's really for algebraic convenience more than anything. With C left and C right, the left and right moving central charges, both greater than 1, he proved that there is a primary operator no statement about the spin here, with dimension delta, which is the sum of the left and right moving dimensions, less than or equal to C over 12 plus a constant, which is something like 0.47.
Does no chiral algebra mean he didn't assume a chiral algebra, or
He assumed there was no chiral
He assumed
algebra.
there was no chiral algebra.
That's any chiral, including like W algebras.
Yeah, higher spin algebras as well.
Right.
But it has Virasoro.
Except for Virasoro, excuse me. No chiral algebra, other than Virasoro. Okay, I'll need one more digit here later. Okay. So that's Hellerman's theorem. It's he said it's a universal inequality, he called it, for any conformal field theory satisfying these assumptions. Very, very powerful statement. I found it very appealing when it came out. Simeon talked about it here maybe more than once even.
Well, at least once.
Spock's, at least once, yeah. So I'm not going to go over too many details of the proof. I'll just point out some salient features just to kind of warm up for
Sorry, can I ask
for
you,
our stuff?
since
Yeah.
you're talking in general, obviously you are using only the torus, but you mentioned, I guess, any Riemann surface will give you some constraints. Does anybody use those? Or
Does anyone what?
if you have genus 2 or 3 or 4?
Well, no, we're only using the genus 1 transformation here. In principle, you could get additional information from higher genus. However, actually, if you, there's an argument that if you show that a CFT obeys modular invariance for the one-loop partition functions, obeys crossing symmetry, and then obeys similar statements for one-point functions, then you can sort of glue all of those ingredients together. So a 4-point function would tell you then about this kind of thing. You could glue this together with puncture toruses and stuff, or other 4-point functions to get an arbitrary genus Riemann surface. So the claim is that modular symmetry of the one-loop torus, crossing symmetry, and a little bit more generates everything, the full mapping class group for all Riemann surfaces. So essentially, this is not only complementary, but it's almost all the extra information there is besides in the crossing symmetry.
What was the statement about one-point functions?
Yeah, one-point functions, if you're in a CFT where you allow non-zero one-point functions, you need to include those two tadpoles.
In particular, one-point
These are
functions on
conformally
the
varied,
torus.
On the torus in particular, yes.
Yeah.
Right.
That's like.
So you need to know what they are, or you need
Oh,
a constraint on that?
no,
Or
you need an
or-
additional modular constraint on
a
those.
modular constraint.
Yeah,
This is like more in cyber.
right. Where's the module? There is. Oh, thank you. Okay. Okay. All right. So yeah. So let me just make another. And one thing this is useful for, besides just telling us a very general fact about CFTs, is it's also interesting from the point of view of three-dimensional gravity, because we know from holography, if you have a CFT with a holographic dual, this is then saying something about the spectrum of the gravitational theory. In particular, it tells you that the lightest massive excitation in three-dimensional gravity, which is dual to this operator right here, has to be, so in 3D gravity, the mass of the lightest excitation has to be less than or equal to 1/4 g Newton. So of order the Planck mass or below. And this is a, Simeon touted this as a kind of a proof of the weak gravity conjecture, according to which you always have to have states in any gravitational theory below Planck mass. Yeah.
So that coefficient 4 is actually some.
That 4 corresponds to this 12
Oh,
here.
I see. Oh, I see. Because you're saying you're using ADS-CFT
Yeah,
in a large C.
we're using the correspondence between C and L in the bulk.
So there's also some finite correction you can
There's
write
a
down
plus order
that's related
lambda
to
to
this
the
one.
1/2. Yeah. Good. We'll come back to this. Okay, so that's one motivation for learning about this. Good, and it can be applied in other areas like string compactifications. You could say, well, if you have a string compactification with a particular value of C, like 18, then this would tell you that you had to have certain states in your string states that were below a certain level. Typically, these are non-BPS states also, so it gives you information about the non-BPS spectrum, the lightest states are. Okay, so I want to just give you a flavor of Hellerman's argument, because I'm going to generalize it. So, yeah.
I'm a bit mystified. In usual, the naive ADS-CFT formula, which relates the mass of a field to the conformal dimension of the operator,
Yeah.
that doesn't involve Newton constant. It only involves the ADS scale. Because
Yes.
Newton constant hasn't. Or maybe it's something special to three-dimensional.
Well, Newton's constant is related to C.
The
C
correspondence
is related to
between the
G.
mass in the gravitational theory and the operator in the CFT is this, where L is the ADS length.
Right. That's the
Okay.
energy and the yes. Okay.
Okay. And the correspondence between C.
Oh, the
and
C
Newton.
C contains Newton constant.
C, all
I got
C
it. Okay.
contains Newton.
Sorry, exactly. Okay.
Okay. So let's write down what we know about partition functions. And what we want to do is we want to show, to study what this implies about the partition function. So let's write down everything we know about the partition function of a general unitary conformal field theory. So in general, you can write it as a sum of terms, each of which corresponds to a primary operator. Okay. Label them by I. And we call each of these terms here conformal block, functions of tau. And each of them is characteristic function. And I'm gonna separate off from here a special primary, which is the trivial, the identity primary, and then have a sum over the non-identity guys. The reason I did that is that the identity primary has a little bit different form of the conformal block than the non-identities. So Z of the identity one looks like actually, let me say first what the primaries, which are not the identity, and we're assuming that there are no chiral currents, chiral primaries other than the identity. So that's going to give us that fact means that we don't have to worry about certain null states, and therefore the conformal block has a simple form. So the form is Q to the HA, where H is the left conformal dimension of the operator. Excuse me, of an operator, where the primary operator A, and then there's a I'm going to put a C over minus C over 24 here, and HA tilde minus C over 24. And let me say that this would normally be C left and C right. Just for simplicity, I'm going to assume that C left equals C right equals C. And sometimes I'll also talk about C total, which is the sum of C left and C right. So that's 2C.
And then a Q bar.
Q bar. Okay, and then these get multiplied basically by these Dedekind data functions. And this guy here has nice modular transformation properties. It's a modular form and some weight. And
so this is always true. If there are null vectors, it won't remove something.
So if you have null vectors present in, among the null relations among the descendants, then it's a little different. So for example, the identity operator is the same here. So HA is 0. H tilde is 0, and then what happens is these sums only run from 2 to infinity instead of from 1 to infinity.
And that's because n minus 1 on the vacuum is the null vector.
Yes, exactly.
But generic characters have no null vectors. That's why you wrote the ZA like that, isn't it?
What's that?
But generic characters have no null vectors, and that's why you wrote the ZA
Characters
like
of non-chiral operators.
I'm just
Yeah.
confused about that. I thought that in general, let's say for rational theories, at least.
I'm sorry, and
everybody had
this is assuming that C left and C right are greater than 1. That's the additional
Okay, so then there
assumption
are
you
no
made,
null
yes.
vectors.
When you worry about minimal models, C less than 1, then you have to worry about all those,
So
yeah.
the constraint that tau that Z of tau equals Z of tau plus 1, isn't that just the constraint? Wouldn't that be implemented by just saying that H twiddle A differs from HA by an integer?
By an integer, yeah, that's right.
So that, but you're.
I,
not
I,
going to-
other than that piece of information, I don't know what else to get out of tau goes to tau plus 1. It doesn't work well with these positivity arguments.
Are there coefficients in this sum related to the multiplicities?
Oh, yeah, I'm there. You're right. There would be in general if you had a degenerate state, but I'm just treating all the states as labeling even degenerate states by their own index here.
Oh, okay. So this sum could run over A's with the same.
Right, exactly.
mononomials.
Typically, yeah, you do have high degeneracies. Right. Okay. So this is a very general form here. This guy here does not transform as nicely under modular transformations because it's missing that m=1 term in the product, and so the constraint of having to put these together in a modular, find modular invariant combinations of these types of functions is what gives us all the information gives us the constraints that we're going to derive. Okay, let's see. So notice just from looking at this partition function that this identity is the ground state operator, and you can read off from here. I should have said that Q is e to the 2 pi tau. So you can read off from here the energy of the ground state. It's just this minus C over 24, I guess, times 2, because the energy is going to be the left moving plus the right moving guy, so minus C over 12, or minus C total over 24, so Casimir energy. And let me also define the conformal dimension is HA plus HA tilde. And so that's related to the energy. It's the energy plus that extra bit there. Okay. So now we'll start. We'll take this expression here, and we'll try to impose modular invariance on it. And the way we do that is we're going to expand around tau equals to I. And David talked about expanding around particular points in UV space, and so we're expanding around a particular point in tau space. And what that's going to give us is a bunch of linear constraints. And in fact, so let's define a new coordinate rather than tau, which is a little more convenient for expanding around tau equals I. Let's define tau equals I times exponential of S. And we'll expand S around 0 then. Okay. So then modular invariance, tau goes to minus 1 over tau, is equivalent to S goes to minus S. Good. Okay. So, and what modular invariance tells us then is that Z of S equals Z of minus S. So Z is an even function.
What is the reason? Is there a reason you're picking I instead of 1?
Well, that's the self-dual point, and
Yeah.
it's just that this, I think it's because this symmetry becomes a very simple symmetry for the S parameter, so it's very easy then to understand what this constraint means. It just means that Z is an even function of S. We wouldn't have that expanding around any other point.
So one way that might involve the tau to tau plus 1 is there is another, the Z3 fixed point.
Yes, yeah.
That's
Yeah, we
a
thought about
combination.
doing that, yeah. And yeah, the problem is the positivity arguments don't work. You can actually push them through if all the spins in the CFT are even. but that's a strong thing to ask in the CFT. and Josh just wrote a paper about, I should say, I didn't even mention Josh, but this is work with my former student Josh Qualls. The first stuff I'm going to talk about is in this paper. And then I'm going to talk about some stuff that hasn't been published, hasn't appeared yet. Okay. So what we do, just like the crossing guys, is we expand Z in a Taylor series in S, and we impose that each of the terms in the Taylor series has to, there have to be no odd terms in the Taylor series, right? So what that means in particular is that if you differentiate with respect to S an odd number of times at S equals 0, this is 0 whenever P is odd. So that's an infinite set of linear differential constraints. And those are the constraints that we want to solve. And you could put these on a computer and solve them using semi-definite linear programming, or you could just see how much, since they are a lot simpler and more explicit, you could see how much you can do with them analytically. And that's what Simeon did. So, yeah, so I could also go back and rewrite these in terms of my original parameter tau. Now I'm going to focus on real values of tau, so I'm going to introduce one more coordinate, or Simeon does, called beta, which is essentially think of as the temperature, this partition function, and so that means the relation between beta and S then is that beta, S is log of beta over 2 pi. Okay, so if you plug that in for S, then these equations can be written in terms of beta. As that for pi. Okay, so you take the partition function with all those Dedekind functions and other garbage, and you apply these operators, and you get a bunch of expressions that look like, for example, some polynomial in the deltas this 2 pi is coming from the q, which is e to the 2 pi I tau. Equals 0. Or rather, sorry, these are the a's, and then there's the identity contribution. That's over on the other side. That's going to be some other function. It depends on just the delta of the ground state, or basically the ground state energy, which is C over 24. Just so it depends on C. Okay, and these f are some particular polynomials. There's an equation like this for every p. Okay, in fact, if p is 3, this will be a cubic polynomial. It's the degree of the polynomial is the value of p.
GP is also polynomial.
Yes. You can take these equations here, and you can try to solve them. You could solve a bunch of them simultaneously, or you could just look at the first couple of them if you're just trying to do this by hand. That's what Simeon did. He looked at the first and the third. And yeah, actually what he did was he took the ratio of the third equation to the first equation. I'm sorry, just for consistency, I want to call this B, not F. I could write down these polynomials for you, but it's totally unilluminating. They're just ordinary polynomials with rational coefficients. Okay? And so for P equals 1, it's just a linear function of delta here and a linear function of C, and for P equals 3, it's a cubic. So you end up with an equation that looks like this for the P equals 3. And you get another equation for P equals 1. And sorry, I do have to get a couple more details here. He takes the ratio of these two equations. Call this one, this index here, B. Then he takes this function, which is just a function of C, it doesn't involve any of the deltas, brings it over to the left side, and he ends up with a cubic polynomial in the deltas on the left-hand side, and a linear polynomial on the bottom. And so let me just call it a cubic polynomial of the deltas. Also involves C, and a linear polynomial down here. And this cubic polynomial has 3 roots. So you can you can estimate the roots from the coefficients of the polynomial. You can say if delta is bigger than any one of those 3 roots, then this polynomial here is always going to be positive if you're greater than the 3rd root. And therefore, this can't be true. Yeah.
Initially, you wrote down the delta was also equal to E plus C. So, in principle, the right-hand side, these B's, these polynomials are
Well,
also
E,
polynomials.
yeah, except where this is the ground state. So E doesn't
so
appear
you
here.
separate
Right,
them.
Okay, so we'll call this here delta plus the largest root of that cubic polynomial there. So basically, in order for this to be 0, there has to be at least one term in this sum which is negative. So there has to be at least one value of delta which is below this root here. Otherwise, all of the terms in the sum would be positive. So it must be at least one operator with dimension delta 1 less than or equal to delta plus. And delta plus you can evaluate in terms of the coefficients here. It's just that C over 12 plus 0.47. So that's how the proof goes. So let me make a couple comments before I go on. First of all, you can improve on this by considering higher constraints. And in fact, Friedan and Keller did this. They went up to the, I think they used about 50 constraints, up to P equals 50 or so. And they were able to strengthen this bound to some extent. They showed if you looked at this is valid for all C greater than 1.
That's a good question.
Yeah.
Everything seems reasonably analytic. Why is 0.7 something that has an analytic expression that is written this way, or is it was just a numerical?
It's actually made out of things like e to the minus 2 pi. Yeah. Yeah. So this No, I'm sorry. Yeah, it's a root of a cubic, or it's related to roots of the cubic.
So it's algebraic or it's
so
analytic,
it's
it is-
algebraic and things like e to the 2 pi. Yeah. Okay, so this is for Dan and Keller's work. They wanted to push this farther by using linear programming and combining the first 50 constraints. And what they showed was that you could constrain delta over C a bit better. Okay, so asymptotically for large C, they found a 1/12 as this limit here. So basically it agreed with this right here. Okay, but for finite values of C, they were able to do a bit better, not a huge amount, and it took an awful lot of work to push it below this line. But, so.
What kind of value is that minimum?
Yeah, it's the lowest that they got is something like let's see, 0.7. No, that's not right. Sorry, no, 0.07. So that's like 1/14. Not much below.
Does the minimum occur at any special value of C?
That's a good question too. It looks like it's at around, it's pretty flat here, no kinks or anything, but it's somewhere between C equals 50 and C equals 100. Let's say C equals 100. Don't know why that should be. That would be your C minimization program, right?
It's not related to
It's not
the
delta minimization.
Oh, delta minimization. Okay.
It's not related to critical dimension
Turn
of the
it
string
around.
theory or anything like this. 26 is in that ballpark.
That's interesting.
Multiple 24.
Okay.
Does anything funny happen as C approaches 1?
As C approaches, so actually this is C below 1 here. C equals 1, you're still, no, hold on a second. Sorry, as C approaches, this just goes to a finite value here. It does not diverge or anything here as C goes to, actually in their chart this is C equals 10. But when C gets to 1, you're basically limited by, you still satisfy Hellerman's bound, and they do a little bit better than this at C goes to 1.
But somehow the whole analysis breaks down if you try to take C below 1, or?
Yeah, because you don't know all the conformal, or the conformal blocks get more complicated, and you have to do Friedan, Q, Shapere, and
For C equal 1, the answer should be known, right? What the spectrum of operators are.
with the
C equal 1. So is there something to compare against analytically in C equal 1 side?
well,
Don't we know all?
we know all the C equals 1s, and they all satisfy Hellerman's bound already, but actually an interesting question I don't know the answer to, maybe somebody here does, is what about the E8 and so forth, the extra CFTs you get at C equals 1, how do they fit into this scheme? Yeah, strictly speaking, I'm not sure they have to, because we assume actually C is strictly greater than 1. So they may not.
Where did that assumption go through in these manipulations?
It was in writing the explicit form for Z and only having these very particular
that
types of
in terms of the
conformal
data.
blocks, and only certain things can happen with null states when C is greater than 1.
So wherein did you use the fact there are no extra conserved currents?
It was because if there had been conserved currents, then we would have had to have additional terms in Z that for operators of, say, dimension HA comma 0, and maybe I'll write those down in a minute for you.
So you
but-
assume there was the identity and then straight HA comma HA bar, which were both bigger than,
Right.
which were both
Bigger than 0.
bigger than 0.
Okay, but those have a little bit different form. Okay. Okay, so so this is one step beyond Hellerman. Another thing you can do, which we did, is to ask, can you say something about the second and the third and the fourth states beyond that lowest dimension operator? And in fact, a very simple extension of Hellerman's argument, in retrospect anyway, allows you to do that. And I'm not sure if I really. Basically, we assume that delta 1, the delta 1 dimension is given, and we plug that in to this expression here. So we have delta 1 and c as fixed inputs. And we want to figure out what is delta 2, the dimension of the next operator. And you can imagine you still have a cubic polynomial here and there, and you do the same calculation, and you find that delta 2 satisfies a very similar inequality. It's less than c total. This is c total, right? C total over 12 plus 0.534. Is it clear what I'm saying we do? We just all we're doing is at first we're extremizing this over delta 1. Then we assume we have delta 1 and c the fixed parameters, and then we extremize delta 2. And so forth, and you work your way up the ladder, delta 3.
Why don't you have delta 1 in the formula?
What's that?
Why delta 2 doesn't depend on what do you assume for delta 1?
Delta 2, oh, this is actually extremizing delta 2 over all values of delta 1 and all values of c. Okay, certainly, if you wanted to take particular values of delta 1 and do some linear programming, then you could get a similar curve to this, and you could constrain the region of allowed delta 2 in that way.
I think that should just be C, not C total. Is C total or 24 or C over 12? Because
C total over 12.
You said,
This is C total also.
okay, I thought you said C total was 2C.
C total is 2c, so
But
it's the
it's-
same as c over 6.
So right now you're not saying anything about the spin.
That's right.
operators.
I haven't said anything about spin.
Can you
In
say something
principle,
about
that might be where tau goes to tau plus 1 comes in, because that is the terms in the, I guess the
But you can't place
Yeah.
constraints on h and h tilde independently, or
yeah, not by this particular method here. The problem is that I guess we're restricting tau to be pure imaginary,
yeah.
and we have to do that so that q, which is e to the 2 pi I tau, which is e to the minus beta, will be positive. And we need that to be positive in order for all these terms in this sum to be positive. If we start trying to separate out spin dependence, then we need to consider this value of tau does not distinguish left and right, and does not do anything for you with spin. But if you wanted to pick out some of the spin dependence in here, then you need to consider non-imaginary tau off in the complex plane, and you would lose this argument completely because these exponentials would no longer be positive. Okay. Now you can do maybe something limited by, say, for example, considering tau as, say, 1 plus I beta over 2, then the even spins would be positive, the odd spins would be negative, so in that way you could get a relation between the even and the odd spins, but that's as far as I've gotten. Sorry, 1/2. In particular, that would get you to the point Philip was wondering about, which is tau equals 1/2 plus I root 3 over 2, where you have the ST cubed symmetry. Okay. Anyway, you get the picture here. This is point 879. But then for delta 4, we ran into a little problem, which was, turns out that the argument here breaks down because in order for this to work, we needed to assume we needed to have not only the numerator be positive, but also the denominator. And it turns out that the denominator is positive up to this value here, but when it gets a little bit bigger, when there's as long as C total is greater than 2 and C is greater than 1, then we don't have to worry about this denominator blowing up. But it turns out that when delta equals 4, the denominator that we end up with blows up at a particular value of C. So we can no longer use our method to derive a bound on delta 4 for any value of C greater than 1. We have to assume now that C is greater than, or C total is greater than 2.34. Actually, even that's not enough, because if it's exactly equal to 2.34, then the right-hand side of the inequality would blow up. So, for example, we could assume, say, that C total is greater than 2.5. And in that case, delta 4 is below C total over 12 plus some other number. So anyway, there is a pattern here, obviously. Everything is C total over 12 plus some small constant. There is also this emerging problem of having to start at a minimum value of C total in order for the argument to work. And so you can imagine scaling this up and deriving a bound for delta n, and that bound for delta n is going to look something like this, plus some small number, but it's only going to work if C total is greater than, and it turns out asymptotically, C total has to be greater than 12 over pi times log of n of the, if this is the nth smallest dimension. Okay. Now it looks like, if it wasn't for this, we could keep going forever and get infinitely many states not too far above C total over 12.
So if C is less than 2 or 2.5, do you think you can violate some of these bounds?
Yeah, I don't know. I don't have examples, but in principle. Okay, so this, what this tells us is at least up to the point where we violate this inequality here, we've got an awful lot of states. So it says that for n less than or approximately equal to e, and this is valid in the large C limit here. E to the pi over 12, pi C over 12. And that's C total. For n less than that, delta n is bounded by C over 12 plus some constant which does not grow rapidly compared to C. Okay. Well, that's actually a much, much stronger result than Hellerman's. It's telling us that not only is there one state below C over 12, there are exponentially many states.
So the constant doesn't grow linearly within or
Well,
anything?
that is a delicate question, actually. I don't have time to go into that, and I have to say that numerically, we believe it doesn't grow as fast as log n, but we couldn't prove that. Okay. So, however, the result I'm going to quote has been proved by other means, and since then, and so we believe it. I think in principle this could be resolved here analytically. Okay, so what that means is there are at least n operators, and these are primary operators, with delta I less than or equal to approximately e to the pi c, excuse me, there are at least e to the pi c over 12 operators with delta below c over 12. That's a lot.
So I know you probably don't want to apply this directly to some example like ADS3, CFT2, because there you have chiral currents, but suppose it just persists in doing that anyway. Is there something you can say about the operators in gravity by taking C large?
Okay, so first of all, about the chiral currents, I don't have time to show it today, but you can extend Hillerman's arguments to include chiral currents, and it has very little effect on the bounds. For example, instead of 0.474, this gets raised to, I think, 0.453 or something like that. That constant bounding delta 1, okay? And so, in fact, all of these just get raised by a very small amount, a couple of percent. Yeah.
It should be raised instead of lowered. I'm just a little confused. It should be a weaker.
Oh,
factor.
I'm sorry. If you have chiral currents. Yeah, sorry. Hold on. I did it wrong. It goes down. I just want to quote you the right number. No, I'm sorry. These are more general theories because we're allowing chiral currents, so the bound is looser. It's a more
That's
general
not
class of
cheating.
theories.
So it
Oh,
doesn't-
7, yeah, 7.5. Yeah.
Oh.
Okay. Yeah, so
Okay, so
that
suppose-
solves that
So
problem.
let me try to use it then for the theory with, the ADS3.
Yes,
old
let's do
dual.
that. Yeah.
And what would you learn from there? These are
Very good. So, suppose we now ask, what does this mean if this particular CFT happens to have a holographic dual? What does it tell us about the spectrum of that gravitational theory? So, yeah. So I already told you what it means to have a single operator of dimension less than c over 12. It means we have a single state in the gravitational theory. So there's a, in the gravitational dual, we know that there is a, originally we had that the lightest excitation had to have mass less than or equal to 1 over 4 g Newton plus some small correction, which goes at 1 over L. And so now this tells us not only is there one light particle below 1 over 4 g Newton, there are exponentially many light states, I should say. Okay, in fact, the log of the number of states with mass less than or equal to 1 over 4 g Newton is, according to this, pi c over 12, which which is the same as pi L over 4 g Newton. And we can compare this to the the entropy of a black hole of mass m equals 1 over 4 g Newton, and that in fact is pi L over 2 g Newton, which is c total over 6, pi c total over 6. Okay, so it's, in fact, this lower bound on the number of states is 1/2 of the entropy of a black hole of that mass. So a black hole state in the gravitational theory would a black hole would satisfy this inequality. Okay. It's nice to have just actually counted these states, enumerated them all, and got the black hole entropy up to a factor of 2. Of course, we didn't assume that there was a black hole here. This could be some other gravitational state. But this says something interesting, which is there's still a minimum entropy, even if you don't have a black hole present, for any gravitational, any state in that gravity theory.
If you took into account the order 1 corrections you dropped, you might come even closer to the actual black hole entropy.
I'm sure we'll get, gray body corrections, or we'll get corrections to the entropy. Oh, you mean would we get actual?
Would you get closer to the black hole value if you took the plus order 1, which you were not writing down?
Oh, I don't think so, because
But
I'm
you've
claiming that in the large C limit, which is the semi-classical gravity limit, that this is not important.
What does it say that it actually scales the same? Like it didn't even have to scale the same.
It didn't have to scale the same, and I only was off by a factor of 2. What I'm going to do next is give you show you another calculation which leads to an upper bound on the number of states in the gravitational dual. And that's actually going to coincide with the black hole entropy.
Upper.
An upper bound. Okay. Good.
Would there have been any inconsistency if you didn't have this factor of 2 difference? Let's say you got the 4.
What's that? If I got the well, the thing is,
could you have gotten these to agree exactly, or
no, I don't think so. I really don't believe they should agree necessarily, because we didn't assume anything about the CFT having a holographic dual in order to get this result.
Mm-hmm.
Okay, in order to get so this is true for any CFT, any large C CFT.
We weigh like too strong, or it would be incredibly surprising. It would be telling us something deep, I suppose. But just the fact that scaling is the same should be teaching.
That's already very surprising that CFTs should have this many. John Carty was very surprised that a CFT should have this many low-lying states. There's a Carty formula which tells you there's a very large number of states with large conformal dimension. But this is a complementary statement about the ones with low conformal dimension.
So these are sort of roughly counting the supergravity states below the black hole threshold. Those go for n of the order of C.
So the black hole threshold actually is the lightest BTZ black hole is pi L over 8 g Newton. Okay, and this is this is actually an unstable. This guy, thermodynamically unstable, and in fact, the lightest stable black hole has this this entropy. This is the mass of the lightest. Where's the mass? The mass. Sorry, 1 over. Okay, this is the mass of the lightest stable black hole. Okay.
But the unstable ones are
The
small
unstable
black
ones
holes.
are
Those
between
small
1 over 8 g Newton and 1 over 4 g Newton. Yeah.
Oh, so the unstable ones can't be arbitrarily small either.
In pure 3D gravity.
Pure
If you have gauge fields and whatever, then it changes, yeah. Okay.
Oh, there is a minimum mass of a BTC black hole in pure gravity?
Yes.
So just one second before you take it on, I just want to compare this to the Cardi formula you just mentioned.
Oh, good, okay.
So you have e to the root c n states there, right?
Yeah, let me compare
And the
Cardi.
Cardi formula applies when n sort of becomes bigger than c.
So
let
the
me-
Cardi formula says, let me just get my factors of 6 here. That the log of the number of states in a CFT of dimension delta looks like that.
Right, and so.
And
let's-
this is valid for delta much larger than C.
Exactly. So let's push it to the border and say delta is order c.
Yeah, so in fact, let's take in this formula, delta equals just C over, and this is the left moving central charge, not the total central charge, so I'm going to say delta equals C over, let me know, okay. Just take delta equals C over 12, which is what we're
Yes.
talking about here. Plug that in there, and you get, this is delta, then C over 24 times C over 6. So the square root is actually, it gives you pi C over 6.
So even though I'm not allowed to use it for that delta, suppose I push it.
Even
to
though
that
you're
delta?
not
Yeah.
technically allowed according to Cardi to use it for
Suppose
that,
you use it anyway.
this agrees perfectly with black hole entropy, and Strominger first pointed that out.
Right.
Okay, for this minimum stable black hole here.
For the minimum stable.
Right. Hartman and Keller and Stoika have proved, using different methods from what I'm using here, have proved that actually the Cardi limit, Cardi bound in the large C limit is valid for delta all the way down to C over 12. It's not valid below that, but it's valid all the way down to C over 12 in large C limit.
And that's what you're using there.
And so in fact, it does work when you plug in C over 12.
So let's see what's the connection between that statement and what you have proved here. If I use the Cardi formula, could I have already said there are going to be that many light states from the Cardi formula itself?
Yes. No, well, actually, Cardi is giving us, yeah, our bound was pi C over 12, so Cardi is giving us
A weaker
twice
bound.
that bound, right?
So that's a stronger answer I can get from there.
No,
From-
theirs is a stronger.
This is stronger.
The pi c over 6 is strong. No,
Sorry, this is,
I see what 12 is stronger.
this is assuming holography. Okay.
That's right. Okay, so that's coming from the gravity. I understand.
Right.
Yeah. So if I just said I know the Cardi formula and I'm willing to push it to delta equals C by 12, which I don't know where I would get it, but suppose someone told me, then I can prove that the CFT has at least e to the pi C over 6 states
Right.
for central charge C and delta less than C by 12.
Yeah. Okay. So I want to tell you about an upper bound on the total number of states, and that's a little bit different argument. But not, I mean, same flavor really. So this is going to be upper bounds on the number of light states, and by light I mean delta less than or equal to C over 12. Okay. So this is actually a much simpler argument than Hellerman's argument, and it's so pretty I want to just show you a little more detail here. So we, I'm not going to decompose into primaries. I'm going to give an upper bound on the total number of states. That makes the argument a little bit simpler. And that's stronger because obviously any primary state is a state, so this will also be an upper bound on the number of primaries.
Last time you were counting only primaries.
Right. It doesn't actually matter for this counting. The spectral growth is in general so rapid, that more rapid than the growth of descendants, that asymptotically the number of primaries and the number of total number of states are agreed for large C. So upper bound, what we're going to do is use again the fact that Z of beta, Z of tau, is Z of 1 over tau, or in terms of beta, Z of beta is actually Z of 4 pi squared over beta. There was a 2 pi in the relation between beta and tau. And we're using the same equation, beta d by d beta, Z of beta equals to 0. And I'm only going to use the first one, so the first order constraint. What that says, if you differentiate the partition function here, I haven't assumed anything about conformal blocks, so this is actually a more general statement. This does not apply, have the same restrictions that I had before. It could apply to C less than 1 as well, although I don't think it would be very useful in that case. So what this means is the beta derivative just pulls down the energy. Beta is, we're expanding around beta equals 2 pi. And we have that simple constraint there to solve. Okay, so I'm going to divide this in two. I'm going to divide this into a sum over negative energies and positive energies. So it's going to be a sum over E less than 0. Let me do the E greater than 0 first. And then there will be a sum over E less than 0. And I'll have a minus sign here. Okay. And notice that since E is less than 0, that's positive. That's positive. Every term on the right side is positive. Every term on the left side is positive. So I have to, what this means is I have to have a balance between the negative energies and the positive energies. Now, what I'm going to do is I'm going to bound the right-hand side here from below and the left-hand side here from above. And that's going to give me this bound on the number of states. And so suppose that E sub n is greater than 0 and E sub n minus 1 is less than or equal to 0. So at the nth state is where the energy changes sign. Then that left-hand side is the sum over I greater than or equal to n, E sub I exponential. Oh, wait a minute. I'm sorry, I want to do the right hand. The negative guys first. Right hand side. That's the sum of absolute value of E and now the largest that this can be is the ground state energy, is C over 24. I'll plug that in. And the same for this exponent. Okay, so all of the terms in the sum are the same. So this is n times c over 24 e to the pi c over 12. And that's c total. Okay. Okay, the other guy, the left-hand side here is a little trickier. What I'm going to do is I'm going to count, consider terms in the sum with energy up to some cutoff. Curly E. So this term in the sum, I mean the function appearing in the sum looks like this, as we all know. There's a peak at 1 over 2 pi. And I want to count how many states there are up to curly E. I'm going to focus on the terms up to curly E here. Okay, so everything in every term in that sum, except for this tiny little bit here, has e to the I x of minus 2 pi ei is going to be greater than or equal to curly E. Right? And this little tiny triangle that I'm neglecting here is from energy 0 up to energy approximately curly E to the minus 2 pi curly E. So not very big. It's a very small range. And in fact, I won't go into the details, but you can actually neglect this completely. And one reason is that these all have descendants in there. We're counting the descendants anyway, so this can hardly make any difference at all. So what I'm going to say then is that the left-hand side is greater than or equal to the total number of states with energy between 0 and curly E times this minimum possible value for each term in the sum. Okay? So what that all means is then that the total number of states in this range is going to be less than or equal to, where is it? The right-hand side was this, nc total over 24, e to the 2 pi c over 24 over this thing here. Over e exponential minus 2 pi e. So that's the same as n over 24 c, well, n times c total over 24 over e times e to the 2 pi, or pi c over 12 plus 2 pi e. So now let's take e to be equal to c total over 24, which corresponds actually to delta is c total, it's e plus c over 24, which is c total over 12. So that means the number of states of delta less than c total over 12 is going to be less than or equal to the number of states of negative energy states times e to the pi c over 12 plus 2 pi e. I'm plugging in e equals c over 24, so this becomes pi c over 6. There. That's the answer I want. That's an upper bound on the number of states below energy E, or with dimension less than C total over 12. Okay, so now we have, putting that together with our other inequality, this was greater than e to the pi C over 12, we have this range in which the total number of states can be for any CFT.
And the right-hand side is the black hole value.
The right-hand side is the black hole value, pi c over 6. So you can't have more entropy than a black hole, which we already knew. But even in any CFT, we can't. So that's not quite true. There's this factor of n in front. So, yeah. That's where all the interesting stuff is. So in a sense, what this is telling us is that the spectrum of very low-lying negative energy states in a CFT determines how big how large this density of states can get, or this number, how many states there can be up to this higher value.
This is the kind of stuff that appears in this, for example, the fairy tale paper where they use the polar part of the modular function to fix the remainder.
It's very similar flavor to that, where the first few terms in the modular function tell you about the whole modular function. We don't have holomorphicity here, so that kind of argument can't be used, but this is sort of a non-holomorphic version of that.
So, just negative energy means delta less than C over 24?
That's right. So we're constraining the spectrum of delta less than C over 12, and in fact for other values, I just plugged that in for comparison, from what the spectrum is for delta less than C over 24. Now suppose you're trying to write down a theory of pure gravity, or as pure as possible, okay? Then what that means is you'd want to, or a CFT that's dual to pure gravity, you want there to be as few low dimension operators as possible. In fact, to first approximation, you'd want there only to be the identity operator, and the stress tensor then gives you the graviton. And nothing else, no chiral currents, no nothing, up to whatever, and make the gap to the lightest state as large as you possibly can. Okay, well, we've seen a limit on the gap, how big the gap can be. But now this is also telling us that if, and the gap actually, the maximum gap is above energy 0. So we should be able to, according to that bound, have no primary states other than the identity with energy less than 0. So this n here should be of order, could be made of order 1 in a pure gravity theory. So pure gravity, in quotes, n is of order 1, and in that case, we really are bounded by e to the pi cm 6.
If you apply to the n equals 4,4 CFT, which is dual to the ADS3, what is little n in that case? Aren't they all the states which are below the remote sector threshold? That looks like a huge number for n in that case.
It's still finite. I mean, it's
Yes,
still small compared to C. It does not grow as fast as C. That's the, or it does not grow as fast as e to the C. It's much smaller than e to the C. So it doesn't contribute significantly to the entropy.
So is this formula true for small c as well?
No. Okay. There is a modification of this upper bound which works for general C, but I was just giving you the simplified thing for large C. Yeah.
So is that modification something you can check in the minimal models, or theoretically
Yeah, in
know the
principle.
spectrum
In principle.
exactly?
Yeah, we haven't done it. Yeah. But since you asked about checking, let me give you an example to close with, okay? So we wanted to test all this out on some genuine large C CFTs.
Just one
And-
sec, sorry to interrupt you again.
Yeah.
I thought in that n equal to 4 case, little n might be as big as e to the root c. And if that were true, would you get subleading corrections? to
Yeah,
the
you get
mathematical-
corrections of order root C, and that's what you expect in general. Yeah. So no, in fact, in even if you just had, forget n equals 4, if you just had the identity operator, all of its descendants up to energy 0 would be of order e to the root C.
Right.
So generally the corrections to entropy will go like root C. Okay. Okay, so I want to study a very simple example, which is one of the simplest examples there is, which is a free boson on a circle of radius r. Okay, and we can just write down the partition function for that thing. Depends on r and of course on tau. That's a Dedekind data function. We have a sum over all integers of q to the, this is the left moving momentum squared here, and then q bar to the right moving momentum squared. And so that's p left, this is p right squared. Okay, good. And this is modular invariant, as you can check if you like. And we know what its primary states are. So first of all, it has these dx and d bar x guys, which generate a U1 current, which are U1 currents, which generate the U1 symmetry of moving around the circle. So this has chiral currents. And then there's a bunch of primaries that look like e to the I, p left, x left, plus p right, x right. Okay. And those have dimension delta equals 1/2 p left squared plus p right squared, which if you plug in n and m there is n squared over r squared plus m squared r squared over 4. Okay, so those are all the primaries. Let's see if this satisfies Hellerman's bound. The way you maximize the delta for the lightest state is by going to the self-dual point. So when r is square root of 2, and delta is n squared over 2 plus m squared over 2. So obviously take n equals 1, m equals 0, whatever you like. The lightest dimension is delta equals 1/2. On the other hand, we can compute C total over 12 plus 0.47. C total is 2. 1/6 plus 0.47 is 0.5. No, what is it? 0.64 or something. And indeed, 1/2 is less than 0.64, so it works. Okay, let's generalize this. That's just a C equals 2 conformal theory. Let's go to a CFT on an n-dimensional torus, d-dimensional torus. Okay, so let's take a, which time do I have? Maybe I skip straight to the more complicated model. I could do the same thing and take a bunch of products of circles. Each one of them has C total equals 2. So I take D of them, then I get a CFT. If I take a boson and a bunch of S's here, that has C total equals 2 times the number of circles, 2 times the dimension. And, but I can be more general than that. I want to actually define the most general toroidal CFT, which is a CFT on a D plus D dimensional Narayan torus. Okay, something we've all encountered in string compactifications. So that means that I am this torus T d plus d is equal to Lorentzian d plus d dimensional space modulo some lattice gamma, which has to be even self-dual for modular invariance.
This is non-unitary?
It's unitary. It's unitary because, yeah, you're worried about the fact that we have, if it's an even self-dual lattice, that means a general lattice vector PL comma PR in gamma is has to satisfy P left squared minus P right squared, has to be an even integer. Okay. But delta is the sum of P left squared and P right squared. So delta, the conformal dimension, obeys the Euclidean norm. And so these are inequivalent, have different dimensions in particular. Okay. Okay. The way we parameterize these, by the way, is so there are a lot of them. There's the d squared dimensional moduli space of these theories, which is locally isomorphic to ODD mod OD cross OD. And we can parameterize that moduli space by a general d by d dimensional matrix. If we break it into symmetric and anti-symmetric components, we call those Gij and Bij. Okay. When Bij is 0, Gij is the metric that defines this lattice here, and basically when Bij is 0, the left and right moving parts of this CFT are isomorphic to each other. Okay. Turning a B field on mixes left and right movers and makes the theory a bit more complicated. Okay, so let's just quickly talk about the dimension of the lightest state in the case when B is 0. Or yeah. So in that case, delta n m, you can show, I'm leaving out a couple steps here, but this is in any string theory textbook, especially Becker-Schwartz has a really nice treatment of this. Is Gij Ni Nj plus G, the inverse metric, Mi Mj. And what M and N are their integers, which are related to the left and right moving momentum. So for example, P left is Ni plus Gij Mj. There's a 1/2 there, okay? P right, there's a minus sign. Okay, so the way that you're going to maximize the gap to the lightest, the lowest dimension operator of this type is by taking Gij to be self-dual. Just a fact, but it makes sense based on that simpler example I showed you, the one-dimensional example. And so, so what we should do is we should take G to be a self-dual matrix. And, and if we do that, for example, you could take, in 8 dimensions maybe, we could take Gij to be the Cartan matrix of E8. We could ask, what is the shortest vector in this case? And the answer is that E8 matrix, the shortest vector, has length squared 2, and so that means delta 1 is the length squared over 2 for the minimum length squared vector is, I'm sorry, length squared is 2. So delta 1 is 1. And Hellerman's bound would give you, in this case, C total is 8 plus 8 is 16 over 12 plus 0.47. It's about 1.8. So Hellerman's bound is satisfied. Turns out to really get close to closer to Hellerman's bound, you need to go to very special situations, very special lattices, which typically only arise in dimensions which are multiples of 24. So the Leech lattice is the first interesting example of this, and that's in 24 dimensions. The Leech lattice has a minimum length vector, I'm going to call that MLV, of length squared 4. And, well, you can plug that in and see Hellerman's bound is still obeyed. You can generalize and go to dimension 24K. This is actually a very difficult mathematical problem. Find a lattice in d dimensions whose minimum length vector is as large as possible. It's a central problem in cryptography theory, and it's unsolved in general. It's been solved up to k equals 13, maybe with an exception for k equals 11 or something. And in all cases, the minimum length squared vector has L squared of 2k plus 2. So that's a conjecture, actually, is that in general there is a lattice whose minimum length squared vector is 2k plus 2.
And how does that correspond?
So how does that correspond? So that's in dimension 24k. So let's plug that in to C over 12 plus 0.47. So C over 12 is, C is, C total is 48k. So C is k over, oh wait a second, no, this is 48k here, over 12, plus 0.47. So we should get 4k plus 0.47 as the upper bound on a vector in one of these lattices. And in fact, I said the length squared was 2k plus 2. Well, 2k plus 2 is less than that. Okay? Still a factor of 2 below it. It's not that satisfying. So you might wonder, could we generalize this and do better? And I only have time to tell you the answer, which is yes, at least by trial and error, we've been able to do better by turning on a non-zero B. And in fact, for the Leech lattice, with B equals 0, you get this, this was k plus 1 here. Anyway, we get much closer to that upper bound for the Leech lattice by turning on.
But what's much closer, like 2K?
4 is less than or equal to 4.47.
When
Yeah.
you turn on B, what's the modular transformation that has this metric?
Modular transformation of
Right. When B is 0, you have G subscript ij equal G superscript ij. But when you turn on B, then
yeah, there's a more general
It's,
condition. Actually, it's G plus B equals G plus B inverse. That's the more general solution.
What about all your other bounds on delta 2 and delta 3 and
Yeah, so good. Okay. So the next thing you want to do with these models is you want to count states. Okay. You can do delta 2 and 3. There's generally a very large degeneracy of states at that first level in these symmetric lattices like E8. So like a 248 dimensional, 248 fold degeneracy for the first excited, the shortest E8 vector, right? Maybe it's 240 dimensional. there are 240 degenerate vectors of length squared 2 in the E8 lattice, and there are scads of them, 190,000 for the Leech lattice. Okay. But let's skip right to the most interesting question, which is how many states are there in these theory with dimension less than c/12? And is that in fact, close to the upper bound or the lower bound, and can we move around between these bounds? So what we want to do to count states, and I'm way over time, so maybe I'll just tell you the answer. It's so interesting though. Okay, I'll just tell you, and I can explain to people privately, that you actually, when you take the large C limit of these theories, of these very special theories with the, which are practically unique, these theories with the maximal minimum length vectors, then you end up with a theory that is in between the lower and upper bounds. It's not equal. We would have liked if it had been exactly equal to our upper bound, then we could have said this is the dual of three-dimensional gravity. First of all, it's not the dual of three-dimensional gravity because it has pure gravity, because it has a lot of U1 factors. All the U1s corresponding to translations in the torus directions will be in there too. So you'll have that's gravity coupled to U1 to the 2D power. Interesting cross couplings between the U1s and so forth. Be nice to be able to get rid of these U1s, but in any case, because of this, it's not what we would call a pure gravity theory. But what we do find is that as you take the large C limit of this type of theory, you end up with a log of the number of states less than C total over 12 is equal to C total times 1/2 log pi e over 3. That number is 0.52306. Okay? And in fact, it's less than C total times pi over 6, which is 0.5236 times C total. But just barely. I don't know why that should be. Which means it's not quite gravity, but it's close. Maybe I better stop. I propose we go to lunch.
So, for lunch, what we'll do is we'll close and lock the doors to this room. So if you want to, you can just leave your bags in here and so forth. For lunch, we'll walk up